So, okay, we finally will start talking about like some neural networks. So, but if you think of like what neural network is really like here I just showing like an example like 2-layer and 3-layer neural networks, right? And in the middle, like if you have an input, like let's say x here, you have the weight in the middle. So here it's just a linear regression, right? And typically you have this here, actually from here to here, it's just like you have, let's say I call h is the hidden layer here. The hidden variable is just like you have your input like a linear combination, maybe add some bias and going through a activation function, right? Let me call it f here maybe. So, and the activation function, like, okay, we'll talk a little bit more about that later on, but typically it's just sigmoid or like 10H or like value, like just introduce some non-linearity, right? So then neural networks, typically you would like to have more than one hidden layer. That's nowadays all of these neural networks, we're talking about deep neural networks, right? So it's just I have more layers. So for example here, maybe I have like this is X, this is H1, H2, and Y here. Maybe this is the final output estimate. So I may have like H1 is equal to W1 X plus B1, and I'm going for an activation function. Typically this activation function, like there are not a lot of choice there. Like as I mentioned, very common maybe just sigmoid. Actually nowadays value will be just like that. Just actually and then maybe I have another layer like H2 is equal to like F W2X, sorry, should be H1 plus B2, let's say, and then I have Y is like W3 times H2, let's say. Here, it depends on whether I have a regression or if I have a regression problem, maybe that's it, right? So I'm trying to have an X here. I just try to, from that features, I want to estimate something, maybe like this is some feature for a home, and then I'm trying to estimate the price for that. Or maybe if I have a classifier, then maybe I will have an extra kind of like activation function. In this case, maybe just I can have a logistic function, for example, like give me the probability whether it's a cat or not. So then you see, like in general, it's pretty simple, right? The question is like, actually, the many decades problem is like, if I give you some input, let's say input x1, y1, x2, y2, and so on, xn, yn as your training data, then how do you train this model, train this one, let's say? So first of all, like, what are the model parameters here? Maybe I should add a bias here also. Maybe add a B3 here. It doesn't matter. What are the model parameters?
W1, W2, B1, B2, B3?
Yes. All these model parameters. So then, like, I really want to select this such that like to fit this way. So actually it's the same as like what we let's see. It's basically completely same idea as like what we talked about earlier for logistic regression and so on. It's still for supervised learning, at least. Essentially, we just need to introduce some loss function, right? So like last time, if this is a regression problem, maybe we introduce this loss function. This is just a square error. So L maybe is the loss. Will be just like I have this this y here minus the expected y there. I don't know, this entire letter, maybe I call it big F here. So I have a big F x I, right? And I want to just add all of this together. I may add regularization. Actually, yeah. Yeah. Yes, square error, yes. Oh, you want, yes, square error is typical, like, because it's more analyzable. So then, like, so of course I can add regularization as well, right? I can, like what we did before, maybe I can add the weights, basically maybe it's hard to see, maybe I add lambda or ci wi square. I just add the total weight there. But regardless whether I add this regularization or not, so then the question is like, how should I change this weight, right? So if I think of this as a mathematical problem, honestly, there's other ways that people think of other ways. For example, like if you heard of those happy and learning, like people kind of in the biology conjecture how we actually learn, like basically it's thinking like if the input and output are firing together, then that will reinforce that love cell, maybe that will be kind of like go more sensitive in the future, so it will more likely to that essentially will be have a higher weight. But since we already set up this loss function here, very obvious things to do is like we want to change this weight here, change the model parameters such that this is to be minimized, right? So, and we show several cases, for example, like for logistic, I guess just for regression, like linear regression, and also like SVM. In a sense, you can tackle this like optimization problem directly. So basically, just take a weight gradient or using constraint optimization, use the KKT condition also kind of, and find exactly what is W1, W2, and so on. At least after some steps, maybe not immediately. But in general, like because this nonlinear function in the neural network, the F here, it's very difficult, like to really try to solve this optimization problem analytically. So then it turns out that like actually it's very interesting. Like this problem like were considered for a long time. I heard stories like even in 2000, like people bring this problem to those optimization people, and they say, no, this is not solvable. This is not convex, not something, and this is you have like 100,000 parameters. There's no way you can optimize that or whatever. Then these neural network people, they do it anyway. They just do the simplest things you can do. So they just do the gradient descent, right? So then assuming that I can find, for example, like for weight, let's say just W1 here, I try to find the gradient of W1 with respect to L, right? So that gives me basically slope of change, how I change W1. If I change along that direction, then my L will increase, right? So if I'm able to find this, then I should just update. How should I update W1?
W1 plus the gradient of W1?
Close.
Just the gradient.
Close. No,
I guess.
no, very close. But think carefully. Very close. What you said, very close. No, Warby got very close, but Wait. We want to increase or decrease the loss.
Decrease.
So the gradient is pointing to where?
Towards the minimum.
No, gradient, the definition of gradient is climbing uphill. So it's pointing up. So that direction is going up. So you want to okay, you just need to subtract that. So then you will subtract the gradient. But of course, this is not, in general, you have this, L is a highly non-convex, right? You can have, for example, if I sketch in 1D, okay, I should have something. If I sketch this function in 1D, maybe something like this, right? So if I am here, if I just, I don't know, maybe, I don't know where I should put it. Yeah, or anyway, I mean, yeah, I think I kind of exaggerating. Maybe here is better. So then I will go down here is okay, but I don't want to go down here too much. I know this direction is up. Of course 1D doesn't mean anything, right? Only this way or that way. But I don't want to go too far away. For example, if I have a step size of here, then I will just go to the next maximum there or something like. So I want to have a reasonable step size. I go in this direction is right, but each time I just go slowly. Maybe I step size this much, then I repeat here, I then compute the gradient again, then move a tiny little bit again, and then continue move, and eventually move to somewhere here. It's only a local minimum, of course. Yeah.
This example is finding local maximum.
No, actually, you always can only find local minimum, right? Because you use gradient descent unless your function itself is convex or concave. Like there's no way you will find the global optimum in general. So it's only by chance actually that the local minimum turns out is kind of okay also. So, and in the sense that it's kind of magical, just do this very simple thing. I mean, works pretty well. So I put the epsilon here, just the kind of step size here. Basically people also call it the learning rate. But that's the high level picture. That's everything about neural network. So, but then okay. At least today we will focus on how to find a gradient, right? So, of course, if you have a reasonable simple problem, you can just compute the gradient directly, right? But in general, even you have 2-3 layer neural network, it become quite complicated. Actually, very complicated. So. Do you know how to do that? Kind of, I have some idea, heard of finding the gradient. So say actually this is an interesting thing. It turns out the solution is extremely simple. At the same time, people take a long time to realize that they're inventing this solution. So in the probably 60 or something, or maybe even earlier than that, maybe in 18 something, those mathematicians definitely they understand that. And and then we invent mostly in 60s, 70s, 80s, I guess. So basically, I think all of you heard of the back-propagation algorithm. So anyway, the idea is super simple because you think of what we are having here. You have your, let's say, loss function eventually depends on your input and some weight, right? But you're interested in the weight. And then you have multi-layer neural networks, right? And your, what should I say? I can kind of split this into intermediate outputs, right? Let's say, let me draw like this. I have W1 here, let's say, and I have W2 here. I should better write like this. I have X, maybe this is hidden layer 1. This is like output like that, very simple. Here I have some connection, I have W1 here, some connection, I have W2 here. Now my loss eventually depends on this Y, right? So my loss will depend on this Y. I can think of like, I have another curve connection, somehow connect from this Y here. Actually, I better draw this Y just have one node, maybe just regression problem to get one Y here, let's say. And this Y will kind of related to this L, right? L will depend on Y basically. Now, I want to find, let's say, the gradient of L with respect to W1, right? And basically, like this, if I think of like L here, I can see that, wait a sec, what should I draw? Okay, for example, I can write some my notation will be complicated. I'm thinking that maybe not the entire W1, just one element inside this weight here. So then I want to take the partial derivative of that with respect to the just W11 here. Now you remember, like in elementary calculus, we have chain rule, right? So if I have this H is kind of intermediate step, that W1 will always have information go through this H, eventually pass to L. Then I will have like W partial L partial W11 will be equal to partial L partial H, and then partial H partial W11, right? Maybe this may not be the best example. Maybe I use this. Use Y. Just make sure I'm definitely okay. Right? Then what I mean is like actually this is just example here, but here I can continue to split. For example, partial Y partial W11 here will kind of related to several of these variables here, actually probably related to H1, H2, and H3, something like that. So my partial Y partial W11 can be split into like partial Y partial H1, then partial H1 partial W11 plus partial Y partial H2 partial H2 plus partial W11, and so on and so forth. Okay. So I mean, in a sense, you can see, maybe just look at this one. You basically, if you can find the partial derivative here locally of the output with respect to the input, then you can basically backpropagate the gradient, or like gradient information from output back to input by simply multiplying. Now maybe I go to exactly one node here. So what I'm saying that if I have this is output is Y, this is X1, X2, then I will have partial L partial X1 is equal to partial L partial Y partial Y partial X1. This may have something else in the future, maybe I mean, may have more nodes connecting to it. You may not immediately get to L. But what I mean is like, if you know parcel L, parcel Y, that is kind of accumulated from far away. Eventually, I pass through here, parcel L, parcel Y. Then, if I want to get this parcel L, parcel X1 to pass back here, it's essentially just simply this whatever derivative that passing back here multiplied by the local derivative, local partial derivative of the output with respect to that input. See what I mean? So this have like parcel L, parcel Y passing back from this node to this node. Then I can pass this one to give like parcel L, parcel X1, let's say, as like this multiplied by parcel Y, parcel X1 here. And similarly, I can have like parcel L, parcel X2 is equal to parcel L, parcel Y. So it's equal to this guy. Now multiply by this output, the derivative of this output with respect to this input here. So I have parcel Y, parcel X1. So this multiplied by this, and then I pass this back here to have the parcel L, parcel X1, X2. And I can keep doing that. If I keep doing that, eventually I will have the partial derivatives for everything, basically, with every variables. It's not just the derivative with respect to the parameters. You'll also have the gradient with respect to each of the inputs, each of the variables as well. So yeah, maybe I just give a very simple example, like just make sure a numerical example, like so let's say if I have super simple example that I have. By the way, this is so-called a computational graph. This is like what I guess for the last decade or so, people just change the way to think about like back-propagation. Once they consider this as something like this, it becomes extremely simple. So in the 80s, people think of okay, try to take all the derivative and consider special case and become complicated. But if you just think of like basically you just have nodes that have inputs going through some computational nodes, and those nodes can compute local derivative. Then what we are doing, the back-propagation, is just passing gradient back and multiply by the local derivative. So let's say if I have a node like this, and let's say I'm just adding these two input together, x plus y here, and then it's something super simple, like and then I multiply z here to get some output f, let's say. So numerically, let's say if I have like x equal to 2 or minus 2 or y equal to 5 and z equal to minus 4, or maybe I give an intermediate name for this guy. Maybe I call this q here. So then, okay, I know it's a super stupid example here, but you can think of like, for example, if I want to find partial derivative for f with respect to everything, then I have partial f, partial q. I don't care about this one. This is just, oh, by the way, f is a multiple, right? So f is actually equal to q times c, right? Okay, let me write anyway. What's partial f, partial q? Not the numerical value. Just forget about the numerical value for that. Just
partial partial f with respect to x times the partial of x with respect to q.
Partial f, partial q is f equal to what? Q times c. Q times. So partial f, partial q is calculus 101. Yeah, just z. Yeah, then
So we don't care about x at all?
X is just the input. It's a
No, we need to care about that,
it's a
but
constant.
partial Q, partial X. Let's compute all the local gradient. Partial Q, partial X is what? Okay. Yeah, this is Q is just X plus Y, so this is partial Q, partial Q, partial Y is also equal to 1, right? So now let me give some numerical value here. Oh, by the way, maybe I let me compute also partial F, partial X first, just the value here. Partial X, if I use the chain rule, it will be what? Equal to partial F, partial Q, right? Times partial Q, partial X, right? So partial Q, partial X is just equal to, it's actually just equal to 1 here. Right. Locally here, yeah, is 1, yeah. Now let me give some numerical values now. So let's say x equal to -2, y equal to 5, and z equal to -4, let's say. So how backpropagation works is that you just go forward, come then backward. Forward, you compute your output, of course, and at the same time you can compute the local gradient, because when you compute the output, you know the local gradient. Right? For example, like here, partial F, partial Q is equal to Z, right? So when you compute the output, actually you see, you can put down the derivative there. And also, actually, I should also write partial F, above partial F, partial Z, I don't use it, so it's okay. Maybe let me write it anyway. Partial F, partial Z is just equal to K, right? So, now let's see. I have this here, the output, so therefore Q is equal to what? Just equal to 5 minus 2, equal to 3 here. At the same time, let me just store the local derivative of the output with respect to all the input. So then for partial Q, partial X is just 1. It's silly, but I just write it down anyway. It's 1 here, right? And then now continue to go like this is 3 times -4. This is like -12, right? And at the same time, can also like compute the local derivative of the output with respect to the inputs. So then it will be partial F, partial Q is just Z, so therefore it's -4 here. And this one, partial F, partial Z is equal to Q, is just 3 here. So then now I can go backward. Go backward is like I can pass back 1 first. I pass back 1 because partial F, partial Q will be equal to partial F multiplied partial F, partial Q. So this is just something dummy, like 1 here, just for the sake of consistent. Like for each node, I just do the same thing. But any question for that? Like I pass 1. Okay, yeah. So I pass 1 here. Then what I'm continuing to do is like extremely routine, right? It's trivial. So what's this gradient now? Partial F, partial Q. From the operator, think of like I'm the computer doing the algorithm. Don't look at the equation here. I have all this number here. What's partial F, partial Q? Yes. So it will be just equal to this passing back multiplied by this guy also. This I have like a 4 here. And so this guy 1 multiplied by 3, I have like 3 here coming back here. So this one, like here, partial F, partial X, then
-4 times -2.
Wait. Here. Not this one. This one is input.
Oh,
yes.
right.
So therefore, like this is just -4 again, right? So then like you just go one time, compute output at the same time, compute the local derivative numerically, and then when you back pop, you just like do this like extremely routine. So yeah, is that clear? I guess. So any question? I let me go through another example, but without drawing here. Like so maybe let's see. This is just what I said earlier. So this is actually just the example I just showed. But okay, this is a little bit more number example. But you see, like again, like what here is already showing the solving the output already. But actually, I don't think it write down the partial derivative for. So this is the input here. Maybe I also write down the. So what's the partial derivative like of this output with respect to like this input here? Oops, I want to get another pen. Okay. So what's the partial derivative of this output with respect to this input? I mean numerically.
-4.
Wait. Here.
Oh, it's multiple. It's -2.
One, right? Oh, yes, 1 or 2, right, wait. That should be. Oh, okay. Oh, okay. You are already doing that. Okay, you're right. That I'm thinking like first it didn't write down the local derivative. I was thinking like to fill in the local derivative first. But anyway, like let's fill in the local derivative. So, but it looks quite a bit. So I think this is like -1. This is 2. This is -2. This is 3. And this is too thick. And this is a 1 here. This 1 here. See, this is what times -1. I guess is -1 exponential. So this. Oops. So what's the local derivative here? Output with respect to input. Are you trying to use the calculator?
E to the one.
Yeah. I think it's already like probably this is 0.37. So therefore, and this one is just this is +1. Wait, +1. X +1. I think it's just 1, right? And then 1/x. So should be 1/x², right? So I guess I don't know the value here. It's 0.73 squared actually. So anyway, like that, I wrote down all the local derivative. So going back, I shouldn't actually. That doesn't mean anything. I write down, then it's disappear. So then like again I just pass back like 1, right? 1, and then like it's 0.73 squared times this is minus whatever from 35553. Then this should be local derivative should be 1, right? So just pass back the same thing. And this local derivative I think is a 0.37. So multiplied by 0.37 is a minus 0.2, and then this one is minus 1, so it's 0.2, and this is just 1 here, so it's just 0.2 pass back, and this is also 1 here, 0.2, and this one is minus 1, so it's a minus 0.2, and so on and so forth. So I guess it's easy enough. And okay, I guess I will just skip here. This is not fair. Okay, let's look at another. Okay, how about value? Maybe couple more example. What's the, if I have value, what do you expect? Like if I have consider I have a value operator. So value is basically just match your input here. So if your input x here, you have output is like this value x is just equal to maximum x times 0. So if it's negative, we set to 0. If it's positive, we set it to just itself. So I have y here. So what was partial y, partial x should be? Always? Yes, 0 or 1. So it depends on the input, right?
Yeah.
So it should be like 0 if like x is negative, or I don't know like whether, or if it's 1 if like 0 is positive, basically. And let's see what else I have here. Okay, like we make example is all with one output, right? How about if I have two outputs here? So I have x here, I have y1 and y2. So I have two gradients passing back, like partial L, partial y1, partial L, partial y2. So how do I find partial L, partial x? Yes, but how to add them? Is equal to.
We have to know the partial y1
Yes.
multiplied y2 divided by the partial x. So we
dy?
have
Oh, yeah.
Yeah, so you can cancel the partial y1 and partial y2.
Actually, that's exactly still like the chain rule in calculus, right? You have like, now you basically have a L, Y, 1x, y2x, right? You have function like that, right? And then you take gradient of that, you will have take gradient L partial y1 and then partial y1 partial x, right? Plus partial L partial y2 partial y2 partial x. So this coming back, you need to multiply the partial derivative of this output with respect to this input, add with this multiplied by partial derivative of this output with respect to this input, then pass back to here. So then Then, okay, more complicated example now. So because we have situation where we have the entire W, right? So for example, if I have input is really a matrix, right? So I have W, or maybe like I think of like X, yeah, X. Y is equal to W multiplied by X, right? Something like that. So my computation unit need the whole W here. So in general, for example, like this is a vector, this is a vector, this is just a linear operation, but maybe I have like some more complicated operation. I have this vector in, vector out. So then I have gradient coming back in. What's the shape of this gradient here? For example, if this is a n by 1, then this is a little bit overloading of the notation. What's the dimension of this guy here? This.
One by n.
Close. Actually, it's the same. It's also n by 1. Yeah, remember that if we need to update eventually, we will update this like act with gradient, right? So the dimension better to be the same, because remember we look, just take that. So now this dimension, here for example this is n by 1. So I have partial. I want to compute that for this partial L partial X is also have the same dimension, n by 1. So how should I get this thing here?
Dr. Sam, are you asking for the dimension?
I'm asking like what should this be? The partial derivative L with respect to X. So how do I compute that? So we look at the scalar case, now we look at the vector case.
Is it the partial of y as it pertains to x, w?
Oh, okay. This is a special case you can think of. This is, yeah, you can use this to give you some intuition. But in general, you can have like a more complicated function here, maybe like inside this circle. But it's just like we know that like the input is a vector, output is also a vector. That's the only thing we know.
Still be n by 1, right?
Yes, the dimension is n by 1, yes. But how do I from here move to go to here? Yes, yes. But what's that called? What's this thing? Or like, so I need to do something like that, right? Partial L partial Y multiplied by this. Yes. So and what's the dimension for this guy here?
You mean the whole thing? Wait,
This thing here.
it should still be
n by n.
Yes, this is n by n. Yes.
Multiply by n by 1.
Oh,
Get
yeah.
the n
Yes.
by 1. So
And so what should be inside then? So let's say y, I call y, this vector is like y1 up to yn here. Oh, sorry, I don't need this under bar here. So y1 up to yn here. And this x here is like x1 up to xm here.
So that should be the x transpose multiplied by 1. That's the matrix.
You want to have a partial derivative here. It won't be just the input and output, right? So you need to have still have the gradient information here, right?
But the x is n by 1 and
Yes.
the y is n by 1.
Yes.
To get the n by n, so we need to use the transpose to get to fix the size.
You use the transpose multiply together, you get the size, but you
So because you are asking what
actually I'm asking what's inside this thing here. You say, okay, it looks like this is something multiplied by this guy, so what is this guy here? You just say this is a chain rule, so I y partial x. Now you know this is should be a m by n matrix, right? So then what was this inside here?
Just be partial y with respect to x1, partial y with respect to x2.
Yes, more or less, right? So I should have something like this is partial y1 over partial x1, right? Then this is a partial, let me make sure I'm correct. Let's see. Partial y2, partial x1, so on up to partial y and xn, x1. And then here go down will be partial y1, partial xm. Right? And you eventually have like partial y and partial xm. Yes. So and multiply by this like have some partial l, partial y1, partial l, partial yn. So this will give me back like this partial l, partial x1. Do you know the name for that? That's a name for this matrix actually. Yes. Now you remember that. Yeah, this is the Jacobian matrix. Yeah.
Do we need to use the transpose to do the multiplication? Because since the partial L over partial X is m by 1,
This is
partial L over partial Y is m by 1. You cannot like multiply them. Multiply two matrices.
Yeah, the way I'm writing is okay. Of course, you can transpose it and put the transpose in.
Mathematically, you have to have a transpose to.
No, you don't. This is look at it carefully. This matrix is n by n here.
Yeah.
This is n by 1. So I got n by 1 back. And this is yn here, up to yn. Of course, you can define the other way and put a transpose there, but it doesn't matter. Like, yeah, but the way writing it here is that you don't need a transpose.
Oh,
Yeah.
okay.
Yeah.
I thought you are like multiply between x and y.
You mean a whole vector? No, yeah. Yeah. So unless like yeah, most of the time like I guess I prefer to use column vectors like many others because it'll be less confusing. So let's see what else. So then we even have this vector. So still okay. Let me. Okay, let's go for a vector example. So it's okay, a real example here also. Like, so let's say I have now then something like I have wx here, so w is let's say n by n, and x is n by 1, so this operation multiply them together. I have q is equal to wx, let's say, and then let's say I have this, I compute the L2 lom here, so that means that like I'm computing q, the lom of q, the square lom basically. And so therefore q, okay, by the way, q is n by 1, right? So let's see, let's compute like the, okay, let's give a name for the output here. I should put a name here. Let's call this output also good. Also just call it f here. So f is equal to q squared here. So the goal here, I want to find the partial derivative for all the partial f with respect to q, w, and so on, right? Partial f, partial q, partial f, partial w, partial f, partial x here. So now let's say I have w is 0, 1, 0.1, just a 2 by 2 matrix. So n, therefore n is equal to 2. This is, I probably better use a finer pen here. So 0.5 is minus 0.3. It's hard to write. 0.8. And let's say x here is equal to 0.2 and 0.4. Okay, so then q, I multiply that, I will just multiply that. Q is equal to 0.22 and 0.26. Now, what's partial q, partial w? Or maybe I start with partial q, partial x first. Maybe this is easier. What's the dimension for that? Partial q, partial x.
Still 1 by 1. N by 1.
Isn't it n by 1?
Wait. We just have this here.
What?
We just have here like
You mean, you mean partial q.
partial x.
The partial of q as it pertains to x is w, right?
Partial q, partial x. Yes, actually you're right, actually, but I want to ask what's the dimension first, but yeah, partial q, partial x actually is equal to w. It's 2 by 2, right? This is like you have to input 2 by 1. We just have this way. The Jacob, that is actually just the Jacobian matrix, right?
You mean,
So the partial dimension
Yes,
of the partial
yes,
partial
yeah, should be 2 by 2, right? Yeah, and actually, if you compute that, like okay, that's essentially this is like some vector calculus. If you have like q is equal to wx here, you want to find partial gradient q. Oh, actually, yes, I don't even know like what kind of notation should I do, because maybe I keep this kind of notation. Q here is actually will be just equal to w. I shouldn't say actually, it should be. You need to go through that. Like that's basically.
take a derivative.
Yeah, maybe I should carefully go through that. So you have this is like q1 up to qn. Let's say this is equal to w11 something, right? And x1 up to xn, right? This is w matrix like that. So therefore, I have like qi is what? Qi is equal to wij xj sum over j, right? then let's say if I try to take a partial qi, partial xk, let's say partial xk, so what will I get? So I basically will have a delta function of kj, right? Only have that one. I have some terms there. So therefore, like, I only have one term, basically, say, wik, right? So partial I, partial xk is wik, so therefore, like, that's the Jacobian matrix, right? Basically, that's the ik element of the Jacobian matrix is ik, wik, so therefore the Jacobian matrix is just equal to w. So does it make sense? Yeah. So this is actually the this is the ik element of this guy here. So yeah. Of course, you can put a transpose, but I don't. I mean, the transpose doesn't matter that much. So yes. Tosa have something to say? Okay, so here, therefore, like locally, there's a derivative. Like I can copy it down. Actually, honestly, I will write it this way. Like oops, maybe I should lower there's some echo there. So so this is W, but like I write like this just for convenience. Oh, Tosa, I guess you better want to like shut down the. Oh, okay, maybe I can do that. Right. The mic. Okay. Oh, maybe I don't. Yeah. Okay. Yeah. So any questions? It's okay, right? So I'll try to let you guys fix your. So any questions? Oh, okay. So the gradient is basically just W, but I write like this because this is more easy to understand. In the sense when I pass back like my derivative like partial f partial q, when I pass it back here, if I pass back partial f partial q, that one because q is 2 by 1, right? So actually these have two elements, right? Partial f partial q1, partial f partial q2, right? So I write like this is more easy to read, because then the gradient passing back to x here is basically this guy multiplied by this guy and this guy multiplied by this guy here. So maybe let me continue to just finish this and go back here. Maybe like just. I have Q is equal to 0.22 and 0.26. So eventually L2 is actually equal to 0.116. Now, as I said, I pass back the gradient. The partial f is just 1 here. And then I should, I forgot to compute the local derivative here. The local derivative for this guy will be partial q square partial q, right? So and this is just equal to q transpose q partial q, this something like that. That actually should give me like 2q. stuff like this. So therefore, like, if I have part 1 here, then this one multiplied by the local derivative is 2q here is equal to 0.44 and 0.26, 0.52. Let me write better here. 0.44, 0.52. Basically, this is 2q. This is the local derivative from this multiplied by this. I got this one here. Then let's say if I want to pass back here to get partial derivative of f partial x, then will be what?
Hello, Dr. Sam.
Yes?
In the in equation, how did you get 0.116?
Oh, okay. 0.116 is equal. Oh, okay. This 0.116 here is like this q square. So the q is this guy here. So actually, I didn't. Yeah, I just write down the number. Sorry about that. So therefore, this is actually equal to 0.22 square plus 0.26 square. Yeah.
Oh,
Yeah.
okay, thank you.
So now going back to, say, trying to find this partial derivative of f with respect to x. So we know like partial f partial q, right? Is equal to this like 0.44.52, then we should multiply partial q partial x. We say this is actually equal to w, right? But write it in a more readable form here. So it's actually the same as w here, or like it's transpose, right? Depends on your kind of convention here. Actually, I should put a transpose. But anyway, so then therefore this one should be just equal to this multiplied by this guy plus this multiplied by this guy, right? And yeah, and that actually gives me minus 0.112 and 0.636, something like that. So yes, and that's also one. Maybe I will just stop here trying to say like what was this one, like what's partial q partial w here? Wait, be careful. Like, what's the dimension there? When I ask dimension, it's kind of ambiguous. I guess I should ask like, how many elements there like, for partial q partial x? Partial q partial w. Total number of elements.
If you take it's like you only have x remain.
Should be two, right? Two. N equals 2.
In this case, n equals 2, so it's 2 by 1.
Okay. How many inputs are for? What's the dimension of w? So it's like 4 elements there, right? There's 4 elements there. So q is 2 by 1, right? 2 elements there. So then partial q partial w. Remember that if I vectorize that, essentially this is a 4 by 1 vector. This is 2 by 1 vector, right? So then partial q partial w is actually the Jacobian, right? So therefore the Jacobian size has to be what? or like the number of elements there.
Wait.
I have essentially like four input elements here, two output elements here. The Jacobians there, remember that matrix. One dimension will be 4, right? The other dimension will be 2, right?
Yeah.
So therefore, like, okay, this become a tensor. Therefore, like, it's kind of complicated. Right? So I just count number of elements. So there will should be 8 elements there, right? So, so then.
If you just treat them as a variable, right?
But this is the main.
No, everything is a variable. Here, like everything you should treat as a variable. Yeah.
I just getting confused with. What's the question again? You're asking like
How many elements
elements?
of the partial Q, partial W here? That's essentially the Jacobian, right?
Yeah.
Yeah, the dimension itself can be confusing, but always think of like, if you vectorize the input and output, then the size of the Jacobian will be like one dimension will be just the number of input, right? The other dimension number of output, right?
Is just 2. You take derivative of that, W will become 1. So 1 times x. The x is just m by 1. So it's 2 by 1. So 2.
No, remember the chain rule here. Eventually, you still need that, right? You still will write partial F, partial W, right? Is equal to partial Q, partial W time.
You
Yeah.
have F here. Okay.
And this partial F, partial Q here, right? So,
That's the thing.
I guess it's easier to think of like this is a single, I mean, instead of like think of like this is Q as a dimension of 2, maybe you can think of that as a have 2 different outputs there. So then maybe like you have a 1 with output Q1, then with an output Q2 here, say. And then I may ask like what is partial Q1, partial W there. Then the size of partial Q and partial W will just have the same size as the W, right? Because in this case, you can think of it like I have again like multiple input but one output here. Then whatever partial Q, partial W, partial Q and partial W is just the Jacobian of this many input and one output. That is basically the size of that is just equal to the size of the input. That's basically W. So okay, maybe I will just stop here. Maybe next time I'll come back and then like just continue with this. Yeah. Yeah.
What is the operation? The name of the operation? Is that like a 2 square?
Oh, this is just the norm of the vector, right?
Yeah, I just
Right.
forgot the name of it.
Yeah. Yeah.
Is that it for today?
Yeah, I guess I will come back next week. Yeah. So,
Okay, see you next
yeah,
time.
yeah, see you next time. Oh, wait a second. I'm sorry. You guys don't go yet. Wait. Just quickly, like as I said, like, oh, did I stop video or something? Oh, wait a second, like.
Oh, no, we're still here.
Okay, so I said like we'll do the lottery, right, for schedule. So, you guys can still see this, right? So I think the code should work. So I just one click and get the table.
Let's run that again.
No, just one time, yeah. So, so okay, you see your presentation. I will put the schedule like on the website also, but yeah, here's your schedule basically.
I had a question.
Okay, we got it.
Yeah.
You said we could do packages. Can we do like a combination of
Packages?
libraries?
Yeah.
Because I was thinking about doing like, not OpenAI, but there's a library called Gym. And
Oh yeah, Gym is interesting also. Yeah,
where
sure.
they do like the
Yeah, sure.
machine
You
learning
can talk
and
about
stuff.
Gym. So it will be kind of like research also, right? So it's okay because it's packaging or packages or research, right? It's okay. If you have some open source you like to talk about, it's fine. Yeah, Gym is interesting. I'm interested to listen to that. Gym is like it's kind of platform to train for reinforcement learning. It's like some kind of playground. So they have some simple experiment that you can train a reinforcement learning model. Yeah.
You have to upload a video, right?
Video for what?
For the presentation.
Why? No.
I think we do the presentation just real time.
Yeah, real time here.
Oh, real time here.
Yeah.
We're talking about
Video is in May.
Yeah.
Oh.
That's much.
No.
Oh, you may of the final project.
We have
Yes.
video, right?
Final project, yes.
I get confused. Like,
The final project is a video?
Yeah. Final project, I will have you guys do video. Actually.
Because that's how we're demonstrating, right?
Yeah.
Like a screen recording?
Yeah.
Oh, you can screencast. It's okay, just a presentation or something.
Yeah.
But
So we're not like we're just emailing.
Yeah.
somebody.
You just email me there.
And then the presentation.
Oh, actually, no. Actually, it's the other way.
Oh, yeah.
I think like okay, that is optional. Report is mandatory. So you write a report for what you do, kind of like I don't know, like white paper, right? You don't need to write exactly a paper format, but just introduction. What you actually do is okay, basically. But optional extra credit you can also hand in a video.
And that's at the end.
Yeah, at the
Instead of
end.
like a final exam.
Yeah. It's like
And then the presentation is just talking about stuff. We're not actually.
Yeah. You don't need to implement anything.
We don't need to do the code.
No, you don't need to. You don't. It would be nice if you just have some demo like showing, right?
Right.
But it's
But
not a
doesn't
must.
have to be like our.
Yeah, it's not
data set. We
not
can use other
original.
people's
Yeah,
code that
yes.
The libraries give and stuff.
Oh,
Yeah.
that makes sense. Okay.
Yeah.
I thought the project is due.
No. Of course not.
Is it like
I don't know.
Yeah.
how like? Are we have it on our computer, or do we bring it on a flash drive and hook it up to that?
Oh, I guess I better to use your computer.
I mean, can we send it to you? Because like I think we have a service, right? We have service. You can, but let's see. What do you? PowerPoint will work. PowerPoint will work. But if you want to do some demonstration, it may or may not work.
So we can do like a combination of PowerPoint. If we have videos, just upload it to YouTube.
Yeah, you can. Yeah.
Video too? Do we need to still do video on this one?
No. I mean, if you really want to, but it's really not necessary unless you really want to. Because I guess if you have a video for 20 minutes, we don't have time.
Well, I mean, if I'm doing gym, it's like
Yeah,
machine
but-
learning on Super Mario Brothers or something. So
Yeah,
it's
if you
that-
have some demo, yeah, like it's okay. Yeah.
But like, how long this should be? Like
30 minutes total?
20 minutes.
30 minutes?
30.
Half an hour.
Half an hour.
So talk slow.
Yeah?
That's
More or less,
long.
yeah.
That's a long time.
So,
No, it's not that long, honestly. It's not that long.
Is it 30 or 13?
30.
Half an hour.
Half an hour, yeah.
Oh, God.
can our presentation include
I-
someone
I'm
on YouTube
not a
talking
native
about it?
Yeah.
What?
I have 3 YouTube videos. Each 10 minutes long.
Yeah.
So,
Yeah.
March 10th.
Yeah.
Okay, great. That's what
I'm not
Okay, really, I stop here.